Okay, in this video, I've chosen an even numbered problem from the text. It's number 14, but this is just focusing on the region and the transformation. So we're given this region R in the xy plane. It's bounded by these four curves, y equals 1 over x, y equals 4 over x, y equals x, and y equals 4x. And we're asked to find a region S that we can map to that in the UV plane. And I want to also find the transformation that sends us there. Okay. So a key thing when I'm looking at a region is to really focus on the boundaries. If I can figure out where the boundaries correspond to, I can figure out what the enclosed region is. Okay. So I notice that these boundaries come in two types. I've got y equals 1 over x and y equals 4 over x. Those look fairly similar. And then I've got y equals x and y equals 4x. Those also, y equals x. Those also look somewhat similar. And often what I'm hoping for is that things will be simple enough that I'm actually just getting a rectangle here. And a rectangle would be bounded by just constants. Well, 1 and 4 are constants. Notice, if y is 1 over x, that means that x times y is 1. Same thing here. If I were to multiply over, x times y would be 4. I'm liking this. Let's let u equal x times y. Then u's going to vary from 1 to 4. 1 to 4. So that gives me that these two curved boundaries here correspond to these two straight line boundaries here. So now I just need to work with these curves, the y equals x and y equals 4x. Okay. And what I'm noticing here is if I were to divide over by x, I'd get the same expression and then have a constant left over. Can I divide by x? Yeah, on this region, x is never 0. We're always to the right of 0. So this is going to mean y over x is 1, and this is going to mean y over x is 4, and I know x is not 0 on R, so that's a legitimate choice. So let's let v be y over x. Then v is also going to vary from 1 to 4. So I'm going to have that those two lines here map to these two lines here, but that just makes S this very nifty rectangle. So I'm focusing on the boundary curves, and I'm looking if there is a pair of them that have something in common, can I take advantage of that to somehow say, with this sort of curve, this thing is constant. Let's make that U, or let's make that V. Okay. All right, now once again, this gives me the formula for the inverse transformation. If I wanted to get a formula for the transformation that comes this way, I would want to solve for x and for y in terms of v, u and v. Okay, so let's see how that works. Here I can see that y is equal to v times x. Okay. Here I can see that x is equal to u over y. Okay. And that's legal because I know that y is not 0 on this region. Okay. So if I plug that in, y is equal to v times u over y. Well, that would mean that y squared was equal to u times v. Now, algebraically, that gives me two possibilities. Y could be plus or minus root uv. But in this case, I can see that the y values on R are positive. So y would be the positive square root of u times v. Okay. Now, that's going to help me get x because we just said that x was u over y, but now that's u over the square root of u times v. So I'm able to manipulate those equations so that I can solve for x and y. Because we're always going to have a one-to-one transformation, it always will be possible to both express u and v in terms of x and y, and to express x and y in terms of u and v. Okay.